In this session, I shall talk about the dot product. I want to prove two things about the dot product. First, let me say how the dot product is defined. If I have two vectors A and B, and if the angle between them is theta, then the dot product, which is written as A vector A dot vector B, is defined as the length of A times the length of B times the cosine of the angle between them. This is the definition. Okay, and from this definition, I wanted to prove two properties. Number one, suppose that A, the vector A, is given by the components AX, AY, AZ, and the vector B is given by BX, BY, BZ. So these are 3D vectors. Then A dot B is equal to AX BX plus AY BY plus AZ BZ. And this is what I want to prove. That's one. And number two, I want to prove that if I have three vectors A, B, and C, okay, if I have these three vectors, so these are vectors, okay, then if I take the if I add B, vector B and vector C together, and I take its dot product with A, then the answer is the same as if I take the dot product of A and B first, and then I take the dot product of A and C, and then I add them together. So this is the property that I want to prove. Just a word of caution, if we look at this expression, it looks very much like the familiar removing the bracket thing that we would do in algebra. In algebra, when if these are numbers, if we have A times bracket B plus C, when we remove the bracket, we would multiply each term in the bracket by the factor outside of the bracket. And that's called a distributive law. And that's what we learn in algebra for numbers. But in this case, we have to be very careful, because the dot here is not the same, is not a multiplication. Okay, despite the name product, okay, the dot here is not a multiplication that we know when we just multiply two numbers, like 2 times 3 is equal to 6. So the dot is actually not a multiplication, even though the way it's written, it looks like a multiplication, and it is called a product. The dot here is something rather more abstract and complicated than just multiplying two numbers, as you can see. So the fact, although it's called a product, it's not really the multiplication of two simple numbers. And because of that, this relation, this distributive law, which is so familiar from algebra, as something that we do when we remove the bracket, this is not obvious at all. In fact, it is there's completely no simple reason or no obvious reason, okay, why this should be true until we prove it, which I shall do. And as in the case of algebra for simple numbers, this relation is also called the distributive law, for the same reason as in algebra, that this term outside the bracket distributes itself to each term in the bracket. Now eventually we'll see that because this dot product obeys the distributive law, and it can be usually quite often manipulated in very similar ways to numbers, to what we would do with numbers when we multiply simple numbers. Right? Because of this similarity, that is one of the reasons why the name product is used for this particular operation. Okay. But even so, we have to be careful that this is not really a multiplication in the simple sense for simple numbers. Right. So having made that clear, let me start with the first thing that I want to prove. This formula for the dot product in terms of the components of the vectors. Okay. Let me draw the vectors again. This is A, this is B, that's the angle theta. One way to prove it is to consider this vector. This vector is the vector B minus the vector A. Okay. and then make use of the cosine rule to relate this length with the length A, B, and the angle. Let me write down the cosine rule. The rule says that the side opposite the angle squared, right, this length squared, is equal to A squared plus B squared for the two sides that contain the angle minus 2AB times cosine of the angle. Right? I shall now substitute the components of the vectors into this equation. Now, B minus A would have components bx minus ax, by minus ay, bz minus az. So these are the three components of the vector b minus a. If I want the length squared of the vector with these three components, I can find it using the Pythagoras theorem in 3D. Just need to square each component and add them up. So that's it. On the right side, I'm just going to keep these terms for now. Next, to see where we are heading, let's take a step back and think about each side one at a time. Now on the left side, we have it in terms of the components of vectors a and b. That's on the left side. On the right side, we still have the terms in terms of the length. But since we have components on one side and lengths on the other side, we should think about how the length a and b are related to the components. For the length a, for example, or for the square of the length a, we could also relate this to the components of vector a using Pythagoras theorem in the same way that I did here. So those would involve the components ax, ay, and az, which are also present here. And in fact, for example, if I expand this, I would actually get a term for the az squared. Okay, and if you look at that, that will give me an ay squared, that will give me an ax squared. And those terms would actually add to give a squared. Likewise for b squared. So we can already see that we are likely to get some cancellation. on the two sides. So with this suggestion, let me expand this and see what happens. That gives bx squared minus 2 of this product minus plus ax squared plus, that would be by squared minus 2 ayby plus ay squared, okay, plus bz squared minus 2bzaz plus az squared. Okay. As I've mentioned, a squared, right, we know this. We know that since the components of a is ax, ay, az, so using Pythagoras theorem, we can relate the length squared to the sum of the squares of the components. So we know that the length of a squared is equal to ax squared plus ay squared plus az squared, and likewise the length of b squared is equal to bx squared plus by squared plus bz squared. Right? Knowing this, if you now compare the two sides of this equation, we see that on the right side we have a squared, and on the left side we can actually pick out those terms from here, here, and here. So therefore, if I can cancel this from both sides, I can subtract this from both sides, and then they are gone, and that's really nice. Likewise, I can do it for b squared and those terms here. B squared is there, bx squared is here, by squared is there, and bz squared is here. Therefore, I can subtract from both sides and those are gone. Now let's take a step back and think about what we want to prove. We want to prove that a dot b is equal to this thing. Alright, where we have corresponding components of a and b multiplied together and then added up. And a dot b itself was defined as in terms of the length and the cosine of the angle. Now if you look at what we have so far, we have on the right side the lengths a and b and the cosine, and on the left side we have the components of a and b multiplied together. Now that looks really promising because that's exactly going in the way that or to the expression that we want to prove. Let me therefore simplify this. Alright, I'm going to write this out again, leaving out all those terms that I have cancelled out. just going to copy it out. On the left side, that's a minus 2ayby minus 2azbz. And on the right, minus 2ab cosine theta. Right, and we can notice that we have minus factors minus 2 on both sides. I can divide both sides by minus 2. This is what we'll get. And by definition, this is the dot product. And this is what we want to prove. So therefore, we have done it. We've proven the first property. Let's move on to the second property to prove the distributive law. Prove that A dot B plus C is equal to A dot B plus A plus A dot C. Since, as I've explained, we cannot just assume that this dot product behaves like the simple multiplying of two simple numbers which are not vectors, because we cannot assume that, because the dot product is not just multiplication, it's something else, something complicated. We need to find another explanation. And to prove it, we are only allowed to make use of what we know, what we are sure to be correct. And that would, at the moment, apart from what I've proven for number 1, we know that that's correct now since we have proven it. The other thing that we know is the definition, right? That was the definition of the dot product. So this is what I'm going to use. I'm going to start from the definition again and try and prove this. All right. So let me illustrate the definition using the vectors and the triangle. Oh no, just the vectors. That's vector A. Let's say that's vector B, and they have a certain angle in between them. Okay, I'll call this theta 1. And I know that the dot product A dot B is equal to AB times cosine theta 1. Right? Now, the vector C, let's say that's A, and suppose the vector C looks like this. it can have a different length and angle from B. Let's say that's theta 2. So A dot C is equal to AC cosine theta 2. Alright. What about that? What about B plus C? Now I've drawn the pictures for each of these separately. Now let me think about this. If I want to draw a picture for B plus C, that's B. Okay, and that's C. If I want to add the two together, one way to do it is to put the tail of C at the tip of B and add them using the vector triangle. This that's B plus C. Okay, and the dot product with A, that's A, let's say that angle is I'll call it theta 3. Then A dot B plus C would be A times the length of B plus C. Right, I'll use this modulus symbol to represent that. Just that length, cosine theta 3. So that's what it looks like. At the moment, it's not very obvious how they can be connected together. But we can find a connection by thinking about the meaning of cosine. If I look at this cosine theta 1 there, I see if between those three, A are the same. Okay. Now if we look at this expression, this equation that we want to prove, on the right side I have this plus this, which is that plus that, and on the left side I have that. Now, as before, alright, we can use my little trick by using this formula that we want to prove to suggest the next step. Now in this case, it is not very obvious if I just look at it this way, but let me try substituting these three into there and see whether that can give us some idea. So this goes into there. Let me write this out. No, that's not that. That's just a number. That's not a vector anymore. These are vectors, but when I take the modulus, this becomes a number. Plus the sum of those two, which are these two. Right, so let me copy those two down here. Right, to be a bit careful here. So that's not a vector. That's not a vector. Oh, right, I just put a stroke there. Okay, so that's just AB cosine theta 1 plus AC cosine theta 2. So that's what it looks like. If I look at these three terms, I see that A is a common factor. So I can divide out the A to make it look simpler. This is what I have. Looking at this, can we perhaps get some idea? Can we somehow show that this plus this is equal to this? Maybe not just from the equation itself. Okay, the terms don't look very meaningful just by looking at it. But if we think about the cosine, right? Let's say if I look at this b cosine theta 1, if I go back to this picture and I think about b cosine theta 1, what does it mean on this figure? If you think about the meaning of cosine, b cosine theta 1 is really, if you think about a right-angled triangle like that, b cosine theta 1 is this length. In other words, it's the component of b along A. Right? Let me call that B1. And C cosine theta 1, cosine theta 2, C cosine theta 2 down here, which we also have here, C cosine theta 2. We can likewise relate it using a right-angled triangle to this length along A. I'll call that C1. Right? So C1 is just the length of the component of C along the vector A. So we do have this physical meaning for those two terms. And likewise, for the length of b plus c cosine theta 3, which we also have here, we can look at this figure and relate it to the same meaning as we did for the previous two cases. The length of b plus c is here, multiplied by cosine of this angle, should be equal to the component of this length along A. Meaning, if I draw a right-angled triangle like that, it would be this length. Okay. So that's the meaning, physical meaning of this. So now we have physical meanings of this, this, and this. And we want to show that those two added together gives this. Now let's think about this in terms of the physical meaning. It means that we want to prove that these two lengths, or these two components, when added together, gives this. Now, how is that possible? How is this length connected to those two lengths? But we can get some idea if we think about how this length, how B plus C, was connected to B and C, connected to the B there and the C there. This is how they are connected, by the vector sum of B and C. So if we look at these two separate vectors which forms these two sides of the triangle, that gives B plus C, then we can relate this side to the component of B along A. And the relation is by forming a right angled triangle. Alright, going to the tip of B and drawing a vertical line or perpendicular line to A. So this length, as we already know, is B1. So that's B1. Likewise, for the C, we know that the component of C along A, which means this, we can likewise look for the component of C in this picture along A, and that would be this length. That would be C1. That's B1 and that's C1. Now let's look at what we wanted to prove again. We wanted to prove that this length, okay, which is the component of B plus C along A, this length is equal to those two lengths added together. But as we have seen, those two lengths are just these two lengths. And it is now obvious that those two lengths, the two separate lengths when added together, will give you exactly this length, which is the component of B plus C. Okay, so in this way, we have proven that this is true. Now to make it more obvious, let me write down write this down in words. This is the component of B plus C along the vector A. That is the component of B along A, and this is the component of C along A. Okay, so this is the component of B along A, that's the component of C along A, and this is the component of B plus C along A. So therefore they are equal according to this diagram, because B, C and B plus C form the three sides of this triangle. And this is true because B, C and B plus C forms a a triangle. Okay, this one, and this completes the proof. We'll stop here.